Imagine a perfectly clear day, blue skies stretching endlessly above us. Yet somewhere high above, invisible processes are at play, setting the stage for perhaps a cloud or even a downpour later. Have you ever considered what needs to happen in the atmosphere for a clear, moist air mass to suddenly turn cloudy? Well, an air parcel reaches its dew point when it cools down to the precise temperature at which it becomes completely saturated with water vapor. At this specific temperature, the air can no longer hold all of its moisture as an invisible gas, and any further cooling will cause the water vapor to condense into liquid water droplets or ice crystals. This fundamental process is governed by the relationship between air temperature and its capacity to hold water vapor. Warmer air can hold significantly more water vapor than colder air. The dew point temperature itself is a measure of the actual amount of water vapor present in the air. When an air parcel cools, its saturation vapor pressure decreases, meaning the amount of water vapor required to reach saturation diminishes. If the air parcel cools to its dew point, its relative humidity reaches 100%, indicating full saturation, and condensation begins. There are several primary ways an air parcel can cool to its dew point within the atmosphere. The most common method is adiabatic cooling, which occurs when an air parcel rises. As it ascends, the atmospheric pressure surrounding it decreases, allowing the parcel to expand. This expansion requires energy, which is drawn from the internal thermal energy of the air parcel itself, causing its temperature to drop without any heat being added or removed from its surroundings. Other mechanisms include advective cooling, where warm, moist air moves over a colder surface, like land or water, transferring heat away from the air, or even radiative cooling, which happens when the ground cools rapidly at night, chilling the air directly above it. An intriguing aspect of reaching the dew point and subsequent condensation is the releases of latent heat. When water vapor condenses into liquid, it releases the energy that was absorbed during evaporation. This latent heat of condensation warms the surrounding air, which can actually make the air parcel more buoyant, allowing it to continue rising. This positive feedback loop is a crucial driver in the development of towering cumulonimbus clouds and intense thunderstorms, showcasing the energetic interplay within our atmosphere. Understanding how an air parcel reaches its dew point is truly foundational to comprehending a vast array of atmospheric phenomena, from the simple formation of dew on grass to the majestic development of clouds and the dynamics of storm systems. It highlights the constant, delicate balance between temperature, pressure, and moisture that dictates our daily weather and profoundly shapes Earth's water journey.
If you love learning about water, like, subscribe, and keep exploring with us.